Now that we've thought about multiplication of integers kind of from an intuitive perspective, let's take a look at the definitions, mathematical definitions for multiplying integers. And again, definitions are rules that are, they just are. Okay, so we say anything times 0 equals 0. That's a mathematical rule. Multiplying by 0 gives you an answer of 0 with integers. Multiplying two positive integers, right? If a and b are positive, they are multiplied as whole numbers. You just multiply them. If a and b, if a is positive and b is positive, then we know negative b, or the opposite of b, is negative. And so in this case here, when you look at this multiplication, oh, sorry, here, is there a typo here? This should be, if a is positive and b is, negative, let's go back to that, right? And b is negative, there's a typo there. And b is negative, then we know the product is just a times b, right? But it's negative, opposite of that. So you end up with that. And then multiplying two negatives, the definitions, negative a times negative b is the same as a times b. And this goes back to see that, and this is the one that usually causes, it's a definition, that's what allows us to do it. But intuitively, again, a reason why that would be true is going back to what we talked about earlier, is that negative 3 times negative 2 would be take away 3 groups of negative 2. And so what you see here in this diagram here is 0, right? 6 negatives, 6 positives. And if we take away 3 groups of negative 2, take away those, get rid of them, take away approach, get rid of it, you're left with what's left over, positive 6. So that's the way that kind of motivates us to have that definition there. Looking at the examples, again, here are the answers. You can use a calculator again, but I just want to make sure you start to get the sense of why they are what they are mathematically, the rules. You will see what we have there, okay, in terms of 5 times 0 is 0, 5 times 8 is 40, 5 times negative 8 is 5 times 8, and then opposite of that. That's the rule from our definition. And then this is equal to 40 there. And again, just like we've been doing, there's properties of this operation with integers, right? The closure property, an integer times an integer is an integer. Commutative properties. Hopefully you're tired by now by that, or not just tired, but appreciative of these rules are not trivial, right? They're not just simple ideas. Now you understand it, but again, as children are learning these things, this is something that is discovered or questions are asked about that. And then the same thing, associative property works, and then there is a unique number, right? 1, anything times 1 produces the same number. And then we have this idea of distributive property also works. We've been using that with number flexibility, but this is also true for integers. When you multiply them, you could use distributive property. There are a couple of proofs that I want you to think about. Again, this is not a, you're not a math major, but I want you to appreciate some of the proofs of some of the reasons why things are, and why would a times negative 1 be the same as opposite of a, right? And so there's a nice definition here. I'm sorry, a nice proof here leading us through that here. 8 times 0 is 0. We know that by definition. If that's true, then 8 times 0 is the same as a times 1 plus negative 1. Because 1 plus 1, this equals 0. So that's a true statement, right? Because this whole thing equals 0. And then you have distributive property. If that's true, a times 1 times 8 times negative 1, then this is true from distributive property, which from our, which we then know a times 1 is just a, and b times 1 is itself. So then we have this. Therefore, we know that a plus a times negative 1, this is equal to 0, since we know a times 0 equals 0. So we have kind of like a transitive property. Now, if this is true, then we know that since these are both a's, then we can conclude that these two are equal to each other. So that's an interesting proof. look at it. I wouldn't even recopy it and write it down and start to think about those ideas. So theorems in mathematics have proofs, right? They're the rules, but they come with a proof. And then you can go ahead and see the proof for this one in the book. But this one was, again, the common one that I like students to understand, or at least be able to reproduce. And then you have another proof. Why is a negative times a negative equal a positive? Why is that theorem correct? Right? It's a definition, but we can prove this one actually. As you see, we can break up these numbers. The associative property allows me to remove these around. Negative times a negative, 1 times negative 1. And so we know that negative 1 times negative 1 is 1. And so then you have this conclusion here. And then you go ahead and then you would finish with these here. Examples here using our rules for products as you multiply. So take a look at it, but make sure, take a look at my notations here of how we do this from our definitions. Again, I want to make sure you're using our definitions or theorems from above to do those calculations there. And then we end with these properties. If you multiply two numbers, integers, and the answer is 0, then one of those numbers has to be 0. That's the only way that you can do that. We use this zero product property in algebra a lot, but it comes to that conclusion. If we know something equals 0, then one of those numbers has to be 0. And then lastly, we know if AC equals BC, multiply two numbers, right, by the same number, then A equals B. You know, this comes up in algebra all the time here. How to solve problems, multiply both sides of the equation by the same number.